All right, so this is ACE Physics Syllabus Code 9702, paper 22 from October, November 2014, question 1, and it reads, the Young modulus of a V metal of a wire is 1.8 times 10 to the 11 pascals. The wire is extended and the strain produced is 8.2 by 10 to the negative 4. Calculate the stress in gigapascals. So Pascal is actually the unit of pressure, and we measure stress also in the same units of pressure. So stress and pressure kind of define the same way. It's the force per area, and a Newton per meter squared is the same thing as a Pascal. That's actually one of the derived units that's contained on that table that's on the slides on in focus. Young modulus, we use the letter E for that in physics. The wire is extended, and the strain, we use the Greek letter epsilon for that, just like we saw an epsilon in the previous example. And then the stress is the Greek letter sigma. It looks like a circle with a little line on the top. And Young modulus is the stress over the strain. Okay, that's the way we define it. Stress over strain is Young modulus. What Young modulus really is, it tells us how strong of a material we've got. It tells us really the strength of the material. An engineer would do an experiment to determine the Young modulus of steel, of any building material, so they'd know like, well, how strong is this material? What weight can it support? Should I build this building out of steel or whatever it might be? So Young modulus is really the strength, in this case, of a metal. And so what we want to do is calculate the stress. All right, stress over strain. So stress here is sigma, and we'll multiply both sides by this epsilon to realize that the stress would be the Young modulus E times the strain epsilon. Now note that strain doesn't have any units. Strain is really like how much longer or shorter something becomes compared to its original length. So like if you stretch a wire, if you like put a force on it and try to stretch it out, it will elongate a little bit. And the strain tells us what fraction of elongation there is compared to its original length. So if it stretches out 1 centimeter, but it was originally 100 centimeters long, then the strain is just that ratio, 1 to 100. So it's expressed as either a decimal like this or a percentage sometimes. A few years ago, scientists measured gravitational waves for the first time. It was an experiment like 40 years in the making. And what they actually measured on Earth here was the strain of space-time itself. And so we have a laser beam that's sort of in a 4-kilometer long tunnel. And as a gravity wave passed by Earth, it sort of changed the strain, okay, of space-time, and the time that it took the laser to sort of bounce off a mirror and come back changed noticeably, enough that we could deduce that it was gravity waves causing that strain in the literal fabric of space-time that we sort of occupy. Really cool stuff. But it shows you kind of how the foundation that you build in physics, even in high school physics, are quantities that are continued to be important sort of in industry and research and beyond. Good stuff. So let's go ahead and make some substitutions. We've got the Young modulus that's given as 1.8 by 10 to the 11 pascals. And the strain is just 8.2 by 10 to the negative 4. And so there are no units associated with it. The units of Young modulus are the units of stress. So see, stress is in pascals, or in this case, they wanted in gigapascals. It's the same thing as the units of Young modulus because there are no units for strain. It's dimensionless. It doesn't have any units. So we just multiply those two numbers. I got 1.8 by 10 to the 11th. 1.8 by 10 to the 11th times 8.2 by 10 to the negative 4. And that gives me a calculator value of 147600000. 147,600,000. I know that you can't see that full number here in the class, but just check YouTube later. I'll rewrite it over here. We get the calculator value 147,600,000. And then the units there are these, pascals. Now we want to convert that into gigapascals. So to cancel out pascals and go to gigapascals, we remind ourselves that there is 10 to the 9, or a billion pascals in 1 gigapascal. Giga means billion. So there's a billion pascals in 1 gigapascal. If we take that number, still in our calculator, and we divide it by a billion, 10 to the 9, we get our answer, 0.15 gigapascals. And so this is how you can convert it. Once you've got it in pascals, we want to cancel out pascals. So you set up sort of a factor where that's in the denominator. The units we want to go to are in the numerator. And you got to know, based on that slide yesterday, all the metric prefixes, that giga is 10 to the 9. There are 10 to the 9 pascals in 1 gigapascal. Part B says an electromagnetic wave has a frequency of 12 terahertz. Calculate the wavelength in micrometers. Here we got to know that the speed of light is equal to wavelength times frequency. So that's the physics that they're expecting you to know, right, to answer this question. We have to know that an electromagnetic wave is light, and light always travels at that speed, c. If I want to solve this for the wavelength, calculate the wavelength, then it's going to be equal to the speed of light divided by the frequency. The speed of light is 3 by 10 to the 8 meters per second, 300 million meters per second. It's about the speed of light, close enough. And the frequency they give up here is 12, and then tera means 10 to the 12. Hertz is the same thing as a reciprocal second. So those units are going to cancel. I'll be left with meters of wavelength. Now, when I type this in my calculator, you have to take care to use grouping symbols when you divide by a value in scientific notation. So take a look how I type this in. 3 by 10 to the 8, right? And there's my 300 million meters per second speed of light. Divided by, open parentheses. If I type this in the way it looks, 12 times 10 raised to the 12, you see how when I close parentheses, it corrects my scientific notation for me. In other words, that's not really correct, right? 12 by 10 to the 12. We're used to seeing scientific notation like that. 12 by 10 to the 12 is the same thing as 1.2 by 10 to the 13. Right? You sort of like take one of the place values out of this and make it an exponent. So your calculator doesn't care that that's technically incorrect scientific notation, right? It's going to take care of it for you. When I hit equals, that gave me the ratio. So the answer is 2.5 by 10 to the negative 5, and the units there are meters. But I want my answer not in meters, but in micrometers. Does anybody know how many micrometers are in a meter? There's 1,000 millimeters in a meter, but there's 1,000,000 micrometers in a meter. 10 to the 6, 1,000,000 micrometers per meter. So to convert this many meters into micrometers, you multiply it by 1,000,000, and we get 25 micrometers. So an electromagnetic wave that has a frequency of 12 terahertz has a wavelength of 25 micrometers. One of the learning objectives that we'll study when we study wave physics is students will be able to state the principal wavelengths of the EM spectrum. So you probably know what the principal wavelengths are, their names, but you probably don't know what the actual values are for their wavelengths, unless you've studied physics before. But you've probably heard of radio waves, microwaves, infrared, red, orange, yellow, green, blue, violet, ultraviolet, X-rays, and gamma rays. Those are all types of light. They're all light. They just exist at different frequencies, different wavelengths, but the same speed. They always travel at the same speed. So by the end of the year, one of your tasks is to know what part of the spectrum this wavelength corresponds to. State the name of the region of the EM spectrum for this frequency. So you can either memorize the frequencies or the wavelengths are really, I think, easier. And I always anchor it to like where we can see between 400 and 700 nanometers. And so this would actually be a little bit longer than the longest wavelengths that our eyes can detect, 700 nanometers. And so this would actually be in the infrared. Okay, that would be infrared light. And that, again, it's a 1-mark question that's, if you've mastered every single learning objective by the end of the year, you'll know that. But that's a really tricky one because it's like, it's just like you have to commit it to memory, like which wavelengths correspond to which, parts of the EM spectrum, kind of tough. And now on to the part of the quiz here, the pop quiz that you didn't realize you were taking a moment ago, part C. there's no question here. It just says an object B is on a horizontal surface, two forces act on B in a horizontal plane, a vector diagram is shown to scale. There really is no question. So we read on, and it says kind of the information that's spelled out on the figure there. A force of 7.5 newtons towards north and a force of 2.5 newtons from 30 degrees north of east act on B. The mass of B is 750 grams. On figure 1.1, draw an arrow to show the approximate direction of the resultant of these two forces. So on this figure, if we were to draw the resultant, the first thing we do is maybe put them head to tail. So instead of these vectors, which are like head to head right here, I'd move this vector over, kind of like that. And then I connect the tail of the first to the head of the last. And so my resultant is going to be kind of like that. Up and to the left. That's the resultant, and they do want you to draw that on the figure 1.1. So we know our answer is going to be kind of like this. Now they want us to show that the magnitude of that resultant force is 6.6. Did anybody get this answer as they worked through it? Did anybody get 6.6? That's okay. We'll all get it together here. So we've got a force of 7.5 newtons that way. And then we got a force of 2.5 newtons this way. And then we got a component that's going this way and a component that's going down. And that angle there is 30 degrees. Because the way that they sort of show us the figure here, 30 degrees, if you translate it over here and sort of construct this triangle, you got vertical angles there. So this is what we need to kind of work with here. We've got a due north force vector of 7.5 newtons, and then we got this hypotenuse 2.5 newtons. I want to resolve this force vector into its x components and its y components. So the x component of this force, so this force 2 here, is moving it sort of to the left and back south. And this side here is adjacent to this 30-degree angle. So adjacent is cosine 30 degrees times 2.5 newtons. That gives me my x component of force. The y component over here down is going to be, it's opposite my 30-degree angle. So sine 30 degrees times 2.5 newtons. 2.5 times cosine of 30. So my left vector is 2.17 newtons. And my down vector is the sine of 30, a half times 2.5. So 1.25 newtons, that's the down vector. What is the sum of the forces in the y direction? (7.5 north plus negative 1.25, or 7.5 up minus 1.25 down, right? Like this vector brings it back down in the y dimension by that much. That's what we solve for. So the sum of the forces in the y direction is (6.25 newtons. Yes? Why would you subtract 2.76? That's the x component. That's the one up here. So this is the one going this way, left. So we got to treat each dimension independently. So we sort of sum everything in the y dimension. That's the 7.5 up, the 1.25 down. This is the one that tells me how far left I went. And that one, I could say, to be very formal, the sum of the forces in the x direction. But there's only one, right? There's only one force that brings this thing left or right. So the left force is this component, 2.17 newtons. Now's the time for that. And you see how I still get the same resultant? Okay, there's my resultant. But now I can calculate its magnitude readily. So I should be able to, in my calculator, go 6.25 squared plus 2.17 squared equals that squared. Right? I'm showing that this resultant is 6.6. So in your calculator, hopefully, 6.25 squared plus 2.17 squared, and then the square root of that gives you R. And let's just do the working. So 6.25 squared plus 2.17 squared equals, and the square root of that, R equals 6.62, which is about 6.6 newtons. So it checks out. Right, you're trying to show that the force is that. It's good to show you're working like this, like what's the sort of value you actually get in your calculator, and then say, oh yeah, which is about equal to what you said it should be. To calculate the magnitude of the acceleration of B, we use Newton's second law. Force equals mass times acceleration, where the force is the net force. Okay, and we know the net force is 6.6. So we can solve for the acceleration as the force divided by the mass. The force is 6.6 newtons. The mass is 0.75 kilograms. Do you see that it's necessary to convert the 750 grams into kilograms if you're going to get meters per second squared of acceleration? Because we know that a newton is a kilogram meter per second squared, not a gram per second squared. So you can't just plug in 750 there. Otherwise, you're not canceling out kilograms. Remember, embedded within that unit of a newton is a kilogram meter per second squared. So to cancel out kilograms, we got to have this in kilograms. That's the idea of base units, and the units always work out, and it's necessary to do some conversions when you plug values into equations in physics. So you actually get, meaningful answers. So 6.6, that's the number still in my calculator, divided by 0.75. All right, there's 1,000 grams in a kilo, so you divide 750 by 1,000 to get kilograms. And we get 8.8 meters per second squared for an acceleration. Just using Newton's second law. Now, the way I worded it on the chalkboard, I asked you to determine the resultant force, to calculate the resultant force. But I didn't say calculate the magnitude of it like they were asking you to here. All right. So I wanted you to calculate the whole vector information. In other words, the magnitude and the direction. And so down here, we're going to have a chance to answer the direction. It says determine the angle between the direction of the acceleration and the direction of the 7.5 Newton force. So the 7.5 Newton force was the one that was going due north. But really, my net force in that direction was only 6.25 newtons, remember? And then my left force over here was 2.17 newtons. So it's the same sort of triangle that I used to show that the net force was 6.6. But now I want to solve for this angle right here, theta, relative to this due north vector, right? Relative to the original 7.5 Newton force, which is in the same direction as this. In order to solve this angle theta, you can use the inverse tangent of the side opposite over the side adjacent. So the inverse tangent of 2.17 over 6.25 should give you the angle there. 2.17 over 6.25. I'm going to take the inverse tangent. You get about 19 and change. So we'd round it to 19 degrees. If you know two sides of a right triangle, right, you can solve for the third one. You can use any trig function to solve for that angle, but you have to use the inverse trig function to solve for the angle. Now, the direction of acceleration is the same direction as the net force, right? Like this was what we called the resultant force, but they ask us about the direction of acceleration. That's Newton's second law. Whatever direction the net force acts in is the direction of acceleration. Any questions about any of that? All right, so that finishes off that question for October, November 2014, paper 22. That was question number 1.